everybody. Welcome to our annual science symposium. Every year we work closely with our faculty advisors and our colleagues to identify an area of focus that is important, timely, and benefits from a multidisciplinary approach. Past topics have included molecular motors. Some of you I know were here last year for that. I recognize some faces. Patterns in nature and climate change. Today's conference convenes leading thinkers on an array of issues related to water. They are here to share their research and recommendations with one another, with many of us who are gathered here in the Radcliffe Gym, and those who are participating today via our live webcast, and with the thousands, I am sure, who will watch that video when it is posted online soon after the conference. You'll be able to access it through the Radcliffe website, and I urge you to spread the word so that more people can benefit from what we are going to hear today. We at the Radcliffe Institute are pleased that our commitment to supporting ambitious new thinking and sharing it with diverse audiences is bringing a topic as important, timely, and challenging as the future of water to such a broad public. And I can't imagine a better issue than water to spill over across departments, disciplines, and audience interests to stimulate new conversations and new collaborations. We'll be hearing today from experts with perspectives from economics, environmental studies, engineering, medicine, public health, agriculture, history, genetics, and more. Speakers in our water lecture series, which is connected to this conference, and you can find out more about that on the website as well, also include an oceanographer and a microbiologist. And you too, our audience, come from an amazing array of places and experiences. A perusal of the list of registrants for today's conference reveals that you are scientists and policymakers, academics, social workers, and community activists, and many more that I couldn't list here. Harvard students and faculty are here, as well as students and colleagues from neighboring schools, and I'll just list, it was really quite stunning to see the list of schools represented here just from our neighborhood. Boston College, Boston University, Brandeis, Clark, Northeastern, MIT, Pine Manor, Simmons, Tufts, and Wellesley. Those are the ones that jumped out at me, and many of you are from farther afield. We all know that water covers more than 70% of the Earth's surface. What is clear today is that water is of interest to more than 70% of fields of study. Take my own field of urban history. I'm a 20th century US historian, and I have particular interest in urban history. I am pleased to see Marty Melosi, an historian and a colleague on the program, and I look forward to his remarks. Although one might not initially assume it, water is a crucial subject for the study of 20th century cities. As I probe how cities and metropolitan areas expanded over the course of the 20th century, questions related to water are key. City planners and city redevelopers had to consider whether the infrastructure was in place to deliver clean, reliable water supply, and what limits and options water or its lack created. Consider Boston. Its growth was inextricably linked to 4 places in Massachusetts you probably have never heard of: Dana, Enfield, Greenwich, and Prescott. The greater Boston area would not be what it is today or have grown as it has without these towns. But by some measure, we are here because they are not. On April 28, 1938, these 4 western Massachusetts towns were officially notified that they were disincorporated, that they would cease to exist. At the time, Boston's growth was straining the water resources available. And on that day, those towns were transferred to the Metropolitan District Water Supply Commission. Soon thereafter, Dana, Enfield, Greenwich, and Prescott were submerged, and they now form the basin of the Quabbin Reservoir, which is one of the largest man-made public water supplies in the United States. Its capacity exceeds 400 billion gallons and is the source of water for Boston and much of the surrounding area. The residential, commercial, and industrial growth of our region would not have been possible without it. In this small example, the politics and engineering surrounding water was deeply interwoven into our region's history. The Quabbin Reservoir story, of course, lies in the past. Today, we will primarily focus on the future, and it is not a simple one. Challenges around the world include pollutants, contaminants, deadly bacteria, overwhelmed governments, and fractious political disputes. The future of water is indeed cloudy. Fortunately, we don't have to look too far to find great minds focused on these problems, and we are grateful that so many of them are here with us today. I look forward to all of you on the panels and our speakers agreeing, arguing, exchanging ideas, and bringing the future of water into clearer focus. Thank you all for joining us today. Thanks in addition to our faculty advisors in the sciences, Joanna Eisenberg and Joan Ruderman, who have organized this conference. Joanna Eisenberg is the director of the science program at Radcliffe. She's a professor of materials science at the Harvard School of Engineering and Applied Sciences. She's a professor of chemistry and chemical biology in the Faculty of Arts and Sciences, the director of the Kavli Institute for Bio-Nanoscience, and a founding core faculty member of the Wyss Institute. Joan Ruderman is senior advisor to Radcliffe's science program and the Marion V. Nelson Professor of Cell Biology at Harvard Medical School. Now it's my pleasure to pass the podium to Joan Ruderman. And again, thank you for coming, and I look forward to a great day.
Thank you, Liz. That was a great way to start off with the big splash. So, water is a vast and vastly important topic that brings us together in 1,000 different ways. Life began in water, and then it stayed there for more than 1 billion years until it could figure out some good ways to emerge onto the land. For most of human existence, water was the major route of exploration and commerce, anchoring both modern and ancient cities. Water crosses boundaries between states and nations. It creates boundaries between them, and in doing so, often creates conflict. Historically, water has been the most convenient dumping place for any kind of waste that we didn't want, as well as unintended vectors for many diseases. You can't turn around without being struck by water in the news, and I offer you just a few recent headlines relevant to some of the topics we'll hear about today from our speakers. The Wall Street Journal headline says, "Drought continues to wreak havoc with crops. Scarce water also has an impact on the price of U.S. crude oil and natural gas," and a good example of the water-energy nexus. The Boston Globe, just yesterday, largest cash settlement in U.S. Superfund history for a Massachusetts harbor. A long-departed manufacturing company will pay $366 million to clean the PCB-laden harbor in New Bedford. From the EPA yesterday, the EPA struggling to keep pace, on the story coming out from the EPA. EPA struggling to keep pace with fracking boom. Congressional auditors conclude in New York new reports that the EPA faces big hurdles overseeing a U.S. oil and gas drilling boom that's creating unknown long-term health risks. Agence France-Presse, Jordanian thirst for water grows. As hundreds of thousands of Jordanians suffer from chronic water shortage in one of the world's 10 driest countries, many complain that Syrian refugees who have fled from the conflict at home are draining the country's meager water resources. The Guardian, textile companies under fire in China over pollution claims. Some of the biggest international clothing brands and retailers have been criticized by a group of Chinese NGOs because of the pollution caused by textile producers that are claimed to be by suppliers. The Baltimore Sun, scientists find more intersex fish in the Chesapeake Bay, and their research suggests one possible source of the gender-bending condition could be the poultry manure that is widely used there to fertilize croplands. Two more. The New York Times, FDA bans bisphenol A from baby bottles. The FDA ruled that baby bottles and children's drinking cups could no longer contain bisphenol A, an estrogen-mimicking industrial chemical used in some plastic bottles and food packaging. Finally, the San Diego Union Tribune from yesterday, Water Authority releases desalination plan. The San Diego Water Authority released its long-awaited draft agreement to buy desalinated water, a deal that could cost more but potentially assure the region of a more reliable source as water supplies across the states tighten. And one last from the Huffington Post op-ed page, time for a 21st century U.S. water policy. So, thank you, and I'll turn this over to Chad Vasitas now, who will introduce Menachem Elimelech. Thank you.
So it is both my great pleasure and honor to introduce to you today Professor Menachem Elimelech of Yale University, or as his friends and colleagues know him, Meni. Meni is globally recognized for his work on membrane separation technologies, in particular reverse osmosis for desalination, as he will speak about today. The research in Meni's lab has also made great strides in other areas, such as particle and colloid deposition and aggregation, membrane fouling and prevention, bacterial adhesion, and what he's getting into today, the water energy nexus. I first met Meni when I was looking for postdoctoral positions. I remember he was looking for a fellowship at Yale, looking for people to apply, and I showed interest, and I received an email from him very late night, or maybe what you'd say early morning, because I think it was about 3 or 4 a.m. I think sometimes he just delays his emails so it looks like he's working around the clock. And so I replied and showed interest, and he said, all right, well, I have some time to speak to you tomorrow morning before I get on a plane. And I remember that phone call because I was sitting on my couch in my apartment in Pasadena, and I answered, and I was immediately overwhelmed by his excitement for environmental science and engineering. It was, his enthusiasm was so contagious that I remember by the end of the phone call, which was only a few minutes, I was pacing around my apartment because I was so excited as well. And thus, I decided to spend my next 2 years of my postdoc under Meni's advice at Yale, where a little over 10 years ago, he was hired to initiate and direct their environmental engineering program, which has been very successful, as shown by that today, it has now evolved into a department. And so I learned a great deal under Meni's mentorship, as well as through his osmosis from being in his group meetings, where all the other students would talk about their work, and just being around the lab. There was so much excitement for the research that was going on. A great example of this is the fact that both of my degrees are in chemistry, yet Harvard calls me an environmental engineer. And so I've been here for 2 years now, and Meni's been a great friend and colleague and mentor for those past 2 years. And so without further ado, Menachem Elimelech.
So anyway, Chad, thank you very much for the kind introduction. I mean, I taught him some engineering, but I learned a lot of chemistry from Chad. And chemistry, we cannot do anything without chemistry. And I'm very pleased to be at Harvard. Not my first time. Again, even though I'm from Yale, I always enjoy coming to Harvard. It's a great place. So today I will talk about desalination. And again, Joan gave the introduction, and I think a few of the excerpts from the newspaper were related to desalination. And I will really try to talk about desalination and emphasize this, what we call now the water energy nexus. Great. So I'll talk about, again, the future of seawater desalination and really emphasize the water energy nexus. I will start with a slide that I always like to start. And again, this week is the Nobel Prize week. And I will give a quote from Richard Smalley, a Nobel laureate of chemistry. He listed here the top global challenges for the new millennium. Again, it's an old article. They were written it just years before he died, unfortunately for cancer. And it's not surprising that you see at the top of the list energy and water. Again, you can have some other lists by other people, and they will have maybe water first, energy, but always either water, energy, water. And as you're going from the see from the list here, many of the challenges here are either directly or indirectly also related to water. And what I'm going to emphasize in this talk is really the relationship between water and energy. They are very, very related, and you'll see it during the talk, and there is no better topic to illustrate this water energy nexus when we talk about desalination. Again, it's well accepted that there is a problem of water scarcity. It's a global challenge. You can read about it in a popular magazine like National Geographic. You can have books about it. And even some coined the term water is the new oil. It's not that I agree with it, because the third talk here by Martin will be water is not the next oil. But again, some people claim that water is a new oil. So it's clear that we do not have enough water. So the question is, how do we get more water so we can supply enough water to the people on the planet? Of course, we need to do all the usual things. We can do water conservation, repair of infrastructure, improvement of catchment, and all of these. But all of these measures will improve the use of water and will not increase the amount of water beyond what we can get from the hydrological cycle. The only way to get water more than what we can get from the hydrological cycle is to turn to engineering. Again, it's my discipline, engineering and applied science. Or either reuse wastewater or desalinate brackish water or seawater. So my talk will focus on desalination of seawater. And I will address the question if it's really one of the ways to combat this issue of global water scarcity. So desalination got a lot of coverage by all kinds of magazines, including some very prominent magazine. Science in 2006 had a special issue on water, and they highlighted desalination as one way to combat against global water scarcity. And here they emphasize the material aspect, the technology, as a way to advance desalination. 2 years later, Nature also dedicated several articles to water, and he emphasized desalination also as a way to cope with global water scarcity. And here in this diagram, you can see the capacity in million cubic meter per year, per day as a function of time. The article was written in 2008, and nowadays we are here, and I can tell you now that indeed the slope that you see here is much, much steeper. Desalination growing roughly to about this slope, much, much steeper than even what predicted. So it's growing very, very fast. Now, there was also a report by the National Academies about desalination here, focusing mostly on the United States. And here they discussed the technology, the economics, and sustainability, and many issues. So those of you who are interested in desalination, especially with the context of the United States, I highly recommend to read this very, very comprehensive report. So the leading technology for seawater desalination, and again, I will talk a lot about it in my talk, is reverse osmosis desalination. In the Gulf country, there are some other technologies that use evaporation, distillation of water, but these are very energy intensive, and all the new plants that are built nowadays, except maybe some of the Gulf countries, are using this reverse osmosis technology. And in this technology, again, this is typical reverse osmosis plant, and the thickness of this line will tell you roughly about the energy that consumed in each stage. You can take seawater by intake structure. It goes some pre-treatment, the way we treat water that you use for drinking water. For example, if you take water from the Charles River and treat it for drinking water supply, it will go through some kind of similar pre-treatment. And then it goes through the heart of the process, which is reverse osmosis unit. These are semi-permeable membrane that in principle will let you only water go through and retain all the salt. And also you have some post-treatment for some other purposes that we may discuss later. And whatever the brine that gets here eventually is discharged back to the ocean. So this is generally seawater desalination by the leading technology nowadays, which is reverse osmosis. So numerous desalination plants were constructed all over the world, and I'll give you some of the prominent examples. For example, in Spain, by this year, they completed a big master plan of 1 billion cubic meter per year. 1 cubic meter is 1 ton or 1,000 liter. It's a huge amount, and again, later we will relate it to energy. And this is mostly for agriculture, tourism, and potable use. Israel, in 1 year, will complete a master plan of 5 desalination plants along the Mediterranean. They completed already 3 big ones, and they will have 2 more, and it will be 0.5 billion cubic meter per year. Again, the reason is there's not enough water, and mostly for agriculture. And I think, in my opinion, for the future, if ever will be peace in this area, water will play a very, very important role, and I think this desalination plant will play a critical role in this aspect. In Singapore, they just finished the second desalination plant. In Singapore, they're already recycling all the wastewater, and now they will have seawater desalination. And the reason they want to reduce their reliance on water from Singapore. They were getting up to 60% of the water from Malaysia, and they want to reduce their reliance on water from Malaysia. So these are some examples. those of you who just want to see how, again, some of are not scientists here, how desalination plant look. This is the example of the one in Hadera in Israel. It's a 130 million cubic meter per year, the largest reverse osmosis desalination plant in the world. And they're just now finishing the one in Sorek in Israel, which will be 150 million cubic meter per year. So this is just close to the power plant in Hadera. It's just south of Haifa. And again, the heart of the process, which are these membranes, they are put here in some kind of a long pressure vessels, and these are the membranes that do all the desalination. So, few words about desalination. In principle, it offers an unlimited and steady supplies of water. The ocean is vast, and whatever desalination plant, you will not deplete the ocean ever. So we have plenty of water. So this is one good thing. Another good thing, you can produce enough water for potable use agriculture without affecting the ecosystem. If you take water from rivers, lakes, and groundwater, you can have adverse impact on the ecosystem. So this is another advantage. However, there are, of course, disadvantages. It takes about 3 to 4 times more energy in the form of electricity to desalinate seawater compared to the way you treat, for example, water from the Charles River or from any reservoirs. And also, there are some concerns, and again, some of them are serious, and again, some are not maybe, about some environmental impacts, and I will touch upon it during my talk. So again, there are some good things, but like anything, there are also some bad things. So last year, I was invited to write a review article in Science about the future of seawater desalination. And in that article, we posed 4 questions, which again, they will guide my talk, and I will show you even some newer data beyond what we presented there. And we addressed the following, what we thought the key questions for desalination. First, what is the energy efficiency and how far you can improve it? Because, and you can hear some people that come with this magic solution to desalinate seawater with 5% of the energy of what you have now, and I want to set all the facts straight here. Secondly, a lot of material scientists go to this area, and the question is, can material science and advances in material science reduce the energy consumption? And I will highlight some of the hot areas of research and what's good and bad about them. Then I talk about some technology. I mentioned that reverse osmosis is currently the leading technology, but let's see, maybe there are some other technologies that can reduce the energy. And lastly, we always need to ask if the desalination is sustainable, and I will try to say a few words about the sustainability of seawater desalination. So let's start with the first question. What is the current energy efficiency of desalination, and how much we can further improve it? And I will start with some data. This shows the energy consumption in kilowatt hour per cubic meter. So if you desalinate and get 1,000 liter, this is the energy in kilowatt hour. Again, those of you who are not engineers, watt hour, again, you can think about 100 watt light bulb, and if you 1 hour, you operate it, this is the energy that will be for 100 times 1 hour. So just so you can get an idea. Now, reverse osmosis technology was developed in the 60s, and the first desalination plant was roughly in the 70s. The energy consumption there was huge, and it dropped dramatically, and nowadays we are roughly about here. So I will zoom on that part, and you see it here. Here you can see a dashed line, and this dashed line describes the minimum theoretical energy of desalination. You can use thermodynamics, and you can just analyze what's the energy needed to just separate water from salt. You assume a reversible thermodynamic process, which in principle, it's not practical. It will be infinite in size. We'll give you just a few drops of water. But again, this is a good reference to start with. And I'm emphasizing that this thermodynamic limit is independent of the process you develop. You cannot come up with another process and tell me, oh, I have a process that can do it better. You can't. So if you do this calculation for seawater, which is about 35,000 ppm, you see that for zero recovery is what % of fresh water we get from the seawater. So if you take 1 drop, which is zero recovery, it will take 0.76 kilowatt hour per cubic meter. But again, it's not practical to have 1 drop. Desalination plants work at 50% recovery. You cannot have more than 50% because then you will need such high pressure and the membrane do not tolerate it. So all desalination plants work with 50% recovery. It means if you have 1 volume of seawater, you will get half as fresh water and half as concentrated brine. And for this, you need about 1.1 kilowatt hour per cubic meter. And as you've seen here, we are about, again, the best RO plant are about 2. Now, emphasizing, this is just for the reverse osmosis stage, just for this desalination through these membranes. So just generally, more about the energy. Again, if you think schematically, this is the membrane, the semi-permeable membrane. You have high pressure pump that uses electricity from a power plant and drives the water through the membrane. This is the energy that you need. And again, you get the product water and some of the pressurized water here, the brine, the concentrated brine, you can recover some of the pressure and use it, and then the brine just discharge to the ocean. Now, putting it in context to the minimum energy of desalination, the way you desalinate, and I showed you this picture of these long vessels, you can think about it that you are in the beginning of the vessel and you have the seawater here. And the seawater, we have a certain osmotic pressure, let's say 25 bars. And as the water goes in the vessel, you start to get fresh water, and then the salinity of the water increases, and this will be by this osmotic pressure. So this is the exit from the vessel, that you get the brine and you collect all the fresh water. So the way you operate seawater desalination, first, based on this diagram, you must apply a pressure at least equal to the osmotic pressure of the brine, because if it's not, the last part of the membrane module, the water will go in the other direction. You will not get desalination. So this is very important when you talk about the minimum energy of desalination. And if you follow just the thermodynamic, the area under the curve is the theoretical minimum energy, which I mentioned is 1.06 for 50% recovery. And anything above, these are the irreversible energy losses that related inherently to this process. Now, in reality, you apply little more than this pressure that equal to the osmotic pressure of the brine, because there are some pressure losses when the water flow in the module, and there is some concentration polarization in which the salt next to the membrane is slightly elevated, so you need a little more pressure. Now remember this one when we talk about materials and if they can reduce the energy, I will refer to this graph again. So let's define another minimum energy. Because we must operate at the pressure that at least equal to the osmotic pressure of the concentrate that come out of the pressure vessel, we can take this pressure and calculate what's the energy that's needed. And the energy, if you do the calculation, is simple. It's just you take the 1 cubic meter of product water times the osmotic pressure, you play with the units, and you can get 1.56 kilowatt hour per cubic meter. So remember this number. This is how we call it the practical minimum energy, and you assume that everything ideal, the pumps and the pressure exchangers, which is not the case. And the best desalination plant, at least what they claim, that their reverse osmosis stage is used about 2. So you can see now that, Jeff, you look at this one of the conclusions, there is some room for improvement, but it's not dramatically. You cannot improve the efficiency by a factor of 2. But there is some room, and any 5 or 10% improvement, when you talk about billions of cubic meter per day, you will translate to a lot of energy. So to put everything into perspective, the thermodynamics tell you it's 1.1. The practical minimum energy, because the way we operate desalination plant, is about 1.6. The best desalination plant, the RO stage, give you about 2. But when you look at the report for all the newly developed plants, what's the overall energy of the entire plant, you see it's between 3 to 4 kilowatt hour per cubic meter. So much more than what you have here. And the reason is, if you look at this plant, there are many other things that you consume energy. You have intake, you have pre-treatment that costs some energy, you have some pumps and all of these. And also there is some post-treatment. This is usually neglected, but many countries use desalination for irrigation, like the one in Israel and Spain. They use a lot of it for irrigation. And it's not enough just to treat the water here, because in seawater there is boron. Boron at the pH of seawater is uncharged and can go relatively easily through the membrane. So in many plants that use water for agriculture, they use additional reverse osmosis stages just to reduce the boron to a low level so they can use it for agriculture. So this consumes more energy. So here I just gave you the big picture of energy, the values, and you can have the right perspective. Now let's see how we can have materials or technology that can really improve upon these energy limits. So let's start with novel materials. Again, there are many material sciences that have brilliant ideas, and let's see if they can be applicable to desalination and if they can reduce the energy. Again, the main challenge now, and the main driving is now force in desalination is really to try to reduce the energy more and more, because there are some environmental impacts that I'm going to to indicate very soon. So one of the hot area of research was what we call high permeability or high flux membrane. And the rationale by these scientists, mostly physicists, chemists, material scientists, was if we create very high permeability membrane, we may not need to have a lot of pressure to drive the force. And because the main energy source is the pressure, you think you can save some energy. And again, we've seen many papers in the last 10 years in Nature, Science, many prestigious magazines about this high permeability membrane. And one of the, again, idea was, for example, to take aligned carbon nanotubes, because through molecular simulation, they found when the water goes through these inside the nanotubes, the rate of transport of water is about 10,000 higher than what you calculate based on a flow in a capillary, based on this fluid mechanics. And they also verified experimentally that you can get very high water flux. But nowadays, I mean, no one was able to show yet that you can get very high rejection that you need for desalination, which is 99.9%, so you can desalinate by one pass. So this is one of the hot area of research. Another relevant area, I will not show you some slides, but aquaporin. Aquaporin, these are the water channels. Also, they transfer water at a very, very high rate compared to the opening of the channel. And the idea that you can incorporate this kind of aquaporin into membranes and create this high water flux membrane. So I will argue that it's not the case and it will not do anything because in reverse osmosis, really what governs the transport, it's not a rate control transport, it's osmotically controlled or thermodynamic control because we cannot operate the desalination plant with a pressure less than the osmotic pressure of the brine. So for example, if you desalinate 35,000 ppm seawater and the 50% recovery, the brine will be 70,000. So here it means you have 70,000 ppm, which translates to 54 atmosphere or 54 bar. So you cannot operate the plant less than it. So even if you put high permeability membrane, you need at least this pressure. And as I told you, you always operate about 10% more because there is some pressure drop, non-idealities, concentration polarization. And it just happened that this improvement in the energy that were done in the last 20, 30 years, the membranes that we have nowadays already work in this range. We already operate at this range with this membrane, and we do not need this high permeability membrane because if you put them, you still need to have the same pressure or the same energy. The only thing it can save, maybe you need less area, but also it will pose a lot of difficulty because if you have very, very high permeability membrane, you get water fluxes which are very, very high, and you will get buildup of salt, what we call concentration polarization, and the flux will drop dramatically. So my argument, this high flux membrane will not be able to do anything to the energy consumption. And what I think you can do more is in the area of improving the current membrane to have them less prone to fouling. And fouling is the process when you have this organic matter, bacteria, anything that accumulate on the membrane and reduce the permeability of the membrane. Now, about the membranes that use for seawater desalination, the gold standard are the polyamide membrane. In the last 15, 20 years, these are the only membrane that used for desalination. There are numerous attempts by all these membrane company scientists to come up with different formulation, and you cannot come up with a better formulation that will give you the high permeability and very high salt rejection that you need for seawater desalination. And again, this is the chemistry, the way you make it. Just notice that you have some amide link here. And this amide link is sensitive to chlorine and other oxidants that I'm going to describe soon. And roughly, when you make this membrane, you have some inherent roughness because of this interfacial polymerization process that involve the diffusion and reaction and create these things. Now, these are the properties of the polyamide membrane that are the best that we have now. We cannot find anyone yet better. And if you look at their property, they have all the properties which are not good for fouling. I mean, some of you material scientists, they talk about anti-fouling surfaces. They really possess all the things that we hope not to have. They're relatively, I mean, they're not as hydrophilic as we hope, as you see from this contact angle. They have negative charge, and we know from, that it's well known that you need to have neutrally charged surfaces to prevent fouling. It's a classic work of George Whiteside at Harvard that showed it on addition of proteins. Also, they have carboxyl group, and carboxyl group can complex organic matter and promote fouling, and they're very rough. In our case, we found that roughness can promote fouling. As I indicated, also, there are chlorine can attack the membrane, and the only way to prevent biofouling is to apply some oxidants, and you cannot do it because it will attack the membrane. And as you know from everyday experience, if you have any wet surface, immediately you get some bacteria grow, even though, there is nothing sterile. So the current membranes, the way they operate, because you have this fouling, you need to increase the pressure beyond what I showed you so you can maintain the same water flux through the membrane. And this increase in pressure translates to more energy. So my argument in this area, and I will not show you, we do a lot of work in this area in our lab, that really, if we think about materials and polymers and so on, we really need to focus on having fouling-resistant reverse osmosis membrane and chlorine-resistant membrane. And such, modification will really reduce the energy consumption because you need less pressure, reduce the amount of chemicals that you need to clean, and so on. So this is addressing the second question of if materials can really reduce the energy of desalination. And the message is high flux membrane will not be the right direction. The right direction will be really to have anti-fouling membranes. So the third question, are there innovative systems and technologies that can reduce the energy of demand? And as I told you, the leading technology nowadays is reverse osmosis. And let's see if we can have some other system that we can reduce. So one way to do it, remember, this is the area under the curve. These are the extra energy beyond the minimum energy that we need to desalinate. And let's see how we can reduce it. There is a way to do it, and you can do the simple analysis. If you take one stage of reverse osmosis, and you get some product water, and then the brine, instead of discharging, you will pump it at a higher pressure to the second stage. And if you have two stages, if you do the analysis, you'll see that you can save this amount of energy. So if I told you the practical minimum energy of one stage is 1.56, if you do two stages, it's 1.28, and in principle, mathematically, if you do infinite number, you will exactly follow this curve. You will approach the minimum energy of desalination. You put three, it will be, even if you put 3, it will be relatively very close. So membrane manufacturers and companies that build reverse osmosis know this trick. They know that you can happen. And unfortunately or fortunately, when they think about desalination plant, the key is not only the energy, it's the cost, the capital cost. And building this thing with 2 high-pressure pumps and so on will not be the solution for them because the capital cost will be quite extensive. And roughly, when you talk about cost of desalination, it's about half capital cost and half energy. But there are some way to reduce it towards this minimum energy of desalination. This is one way. I would like now just to highlight another process that we work in our lab. We develop a process we call forward osmosis. And I will show you some idea that how it can be used maybe to reduce the energy of desalination. And in this way, the idea, if we can utilize waste heat. So here we go to thermal processes. If you can find some waste heat that comes from a power plant, if we can use it as the energy to drive the process, then it may be good. And one way to do it in this forward osmosis, if you have this semi-permeable membrane, again, we have seawater on the other side. Instead of pressurizing it by hydraulic pressure, on the other side, we can put another solution of high osmotic pressure. So water will flow naturally from the seawater to another salt, but then if you move to another salt, if you cannot separate it, so you don't do much. But if you can come up with a solution that we call thermolytic draw solution, if you find a solution that you can decompose the solution and separate the fresh water from the solution by applying low-quality heat, then it can work. And again, one example that we have in our lab is the ammonia carbon dioxide draw solution, and we are working on this. So if you take ammonia and CO2 and dissolve them in water, you can get ammonium salts that create high osmotic pressure. These are ionic species. And then the fresh water will move to this high osmotic pressure from the seawater across a semi-permeable membrane. And if you apply a waste heat at atmospheric pressure, you need 58 degrees. And if you have slight vacuum, it can be much lower. Then you can convert these ionic species again to ammonia and CO2, and then separate them and get the fresh water. So I'm emphasizing here you will need much, much more energy because thermal processes are not efficient, but all this energy will come in the form of waste heat from a power plant that otherwise cannot be used to produce electricity. It's just In the steam turbine, this is the waste that they hit at the end of the turbine, and you cannot do anything with it. So usually you just discharge it to the environment. So lastly, I would like to go to the last question. Is seawater desalination a sustainable technological solution to global water shortages? And just to remind you, all the interactions of seawater desalination plant with the environment. We have a power plant that produces the electricity, and you see by the thickness of the line, reverse osmosis is the largest consumer of energy. You have pretreatment, and so on. So the interaction with the environment will be through the power plant and greenhouse gas emissions, intake structure that can affect some aquatic organisms. Also, we'll have a discharge of the brine to the environment, as you see here. And you can see here the first one of the intake, it's impingement and entrainment. You can control it by right intake. You have submerged intake, sieving, and it's not, again, it's a problem that you can overcome. The greenhouse gas emission can be significant, and I will show you the last slide some numbers. And also brine discharge. You can discharge to the ocean brine which is twice as much concentrated in seawater, and it can create a lot of problems. And unfortunately, there are not enough extensive data in the field to show the impact, although we know that there is some impact, but we are not sure how far is the impact or how severe. But from engineering point of view, if you locate the plant appropriately and you have designed a diffuser that discharges the brine to the ocean in the right way, you can overcome it. So the last slide, just before conclusion, the major hurdle for implementation of desalination is energy. And again, in California, you mentioned this desalination plant, the one in Carlsbad, it took them 12 years to approve it. So, and the same way. So let's have some numbers. Typical reverse osmosis plant between 3.5 and 5 kilowatt hour per cubic meter. These are the existing plants. We know how much kilowatt hour per cubic meter you need for seawater, so we can calculate how much CO2 produce. And the CO2 emission will be, if you use just the typical power plant, 1.6 kilograms CO2 per cubic meter of fresh water. Let's now take example of Spain. 1 billion ton per year. It translates to 4,000 gigawatt hour per year, or 1.6 billion kilograms CO2 per year. You can do some calculation, what the equivalent of how many cars you add to the street, and it'll be a huge number. So anything in desalination, even if you improve 5 and 10% the energy efficiency, it still would be a major contribution. So some conclusion. As I argued that real gains in desalination can be realized by development of fouling and oxidant-resistant membrane. The idea to have high flux membrane will not work for desalination. It's not the right way to go. And although I did not mention it, but I mentioned briefly that this removal of boron, that you need to have these extra desalination stages. If you can find a membrane that can get higher rejection, it will be much better, but it's a problem because the membranes operate on a mechanism that we have what we call the selectivity permeability trade-off. If you try to make it more selective, it will be less permeable to water. So you cannot improve the water and the selectivity at the same time. And you cannot sacrifice the selectivity because if the permeability is reduced, you need more energy for desalination. So because it's for the broad audience, I thought to have some recommendation which are more like the last slide. So as I said, we can have many, many other options for having more water, but like conservation and so on, but these options alone will not be enough to meet the water demand that we have nowadays. This is one conclusion. The second one, while seawater must be considered after all other options have been implemented, as I indicated, it still should be viewed as a crucial component of the portfolio of water supply. You cannot say that it cannot be used at all. It's a portfolio of water supply, and there is some room for desalination to somehow. And lastly, for water-scarce countries that already implement all the other measures, desalination may serve the only viable means to provide the water supply. There is no other way to do it, and this is what's happening in the Gulf countries, in Israel. Some other countries are argued they can maybe do it better, but this is a topic for discussion. So we'll end up with a thanks for the funding agencies and all the group, and thank you very much for your attention.
Thank you, Meni, for the wonderful talk. Are there any questions? please. Please come up to the microphone and identify yourself.
My name is Simon Chung. I'm a grad student in chemical engineering department at MIT. My question is, the 10 to 20% in higher operating pressure, is that to account for the fouling effect, or the fouling effect costs much higher than the 10 to 20%?
The 10 to 20% are without fouling, just because you have pressure drop and the water flow within a 6-meter channel, and the concentration polarization that always happen when you permeate water but retain the salt. So without fouling. With fouling, you need more.
Like how much more?
In the treatment plant, usually in desalination plant, when the about 10% increase in pressure, they stop and clean the membrane. So it can go up to 10%. Okay. And then at that point, when it reaches 10% more increase in pressure, they stop and clean the membrane aggressively by chemicals. And again, it's not sustainable. You need to have very toxic chemical, EDTA, surfactants, and all so on.
Thank you.
David Jackson, Radcliffe Institute. It's clear that there are some very significant concerns with respect to the amount of CO2 that's produced using electric power for desalination. Have you looked at both either the financial and technological feasibility of using power sources such as wind or solar built in conjunction with major desalination plants that might avoid that problem, or at least reduce it?
It's a good question that always comes. It's very difficult to work with desalination in sources like wind and solar that are not steady. You need to have steady supply. So in Australia, for example, they claim that the desalination plant is operated by a wind farm, but what they do, the wind farm produce electricity and give it to the grid, and then they take the electricity from the grid. So in my opinion, I mean, it's not a solution because you still need to use electricity. If you can develop a desalination process that uses less electricity, it's better to use this green energy to give it to the grid and use it for a process that can use less energy. So now also another idea that we suggested in a science article, that one way is if any utilities, municipality, or country want to build desalination plant, you can tell them, okay, if there is no choice, we need to build it, let's build an equivalent amount of green energy that you will provide to the grid, and then we will let you build a desalination plant.
Okay, thank you very much. It's really impressive what we've been able to do with desalination. But I still see it as a short-term solution, not as a long-term solution, because sooner or later the energy and the green gases, greenhouse gases are going to be a problem, and the amount of brine that you're going to put back into the ocean is going to have an effect. So I really kind of feel like a lot of people say, oh, don't worry, we're going to have desalination that'll solve our water problem. And I just want to say that it is a partial solution, but I just want to know what your feeling is about, kind of what else can we do, and how do we have to see this as a part of a bigger solution? I
mean, I agree with you. One of the conclusions, you need to have it only as a last resort. It happened again, and I travel a lot in Asia and in some other countries, and many emerging countries or countries that want to feel that they're good, they feel that they need to have this desalination capability, almost like to have a nuclear capability to show that you're really advanced technologically. My approach is really as a last resort. And if you cannot do it, again, we cannot live without water. But if you have some other options, try them, because of the reason that you mentioned, a lot of electricity and some environmental impact that we still do not understand exactly what's the impact, but I'm sure there is an impact. Good question.
Hi, Professor. My name is Abdullah from the Technology and Policy Program at MIT. And actually I had a question on the brine impact. So I know you kind of said there's a lot of uncertainty regarding that impact. But my question is, do you think that it could potentially be not a showstopper, but a potential limit to the use of desalination, especially in a place like the Gulf, where you have a semi-closed body of water and like 5 or 6 countries relying heavily on discharging brine to this closed kind of body of water?
Yeah. I mean, although I said that the ocean is vast, but you're right, in the Gulf country, there is some research that showed that the salinity of the area around the desalination plant increased. But there are some other approaches. For example, in our case, we also do research to use this brine for a beneficial effect. And in principle, we can harvest energy from the brine. When you have seawater desalination, you need energy to separate water from salt. But from thermodynamics, if you have mixing fresh water with salt, you can harvest the energy And we think about, it's a process that's called pressure retarded osmosis, to use brines and then treated wastewater, and this salinity gradient, you can produce electricity. And by this way, you can even dilute the seawater. But for some closed area like the Gulf, there is some evidence that there is some effect. For vast ocean, if in San Diego, there'll be no effect on the salinity there.
Hi, my name is Jong Ho Lee from MIT.
Everyone from MIT, or what's happened? There are no engineers at Harvard?
Yeah, you mentioned that the high permeability membrane is not a good solution, but doesn't it, you already mentioned, but doesn't it significantly reduce the capital cost by reducing the plant size or membrane size or those?
In principle, if you can make this Li nanotube the same cost of this polyamide membrane, it may reduce the cost, but it's not significant. In seawater desalination, the membrane component is only 3% of the total cost. So it's not significant. Also, you cannot operate high flux membrane. This phenomenon of concentration polarization for the engineers here is proportional to the exponential of the water flux over the mass transfer coefficient. If you just double or triple the water flux, concentration polarization will be so severe, so the salt that the membrane surface will see will be 10 times like the seawater, and then the flux will decline. So it's not a solution.
I'm David Anik from Harvard Medical School, but also I'm here more as a community activist, and you focused in some sense on the economics of this, but I think my perspective is more looking at how centralized production and control of water has caused problems when it's privatized, and it leads to problems with higher costs and poor maldistribution. And so I'm just wondering if there's anything that is along the lines of small-scale desalination, similar to maybe small-scale solar or regionally distributed wind power. In other words, the centralization could itself become, the idea is that we think, oh, big plant produce a lot of water, that'll serve everybody. In real life, often the centralized sources of production end up adding to distribution inequalities in a society. So I'm just wondering if there's anything along the lines of small scale that would decentralize production when you're thinking about that bigger problem that often occurs. Because engineering-wise, this is fine, but politically, economically-wise, this could also add to other problems that we already see. So thank you very much for any thoughts on that.
I emphasize only large-scale desalination plant, and they follow the centralized approach of water distribution. There are some papers and some installation of a small-scale desalination plant in remote area, and these are the ones that can be operated by, thermal energy, solar and wind, and because there is no grid there. But there is an economy of scale. When you have small plant, the energy consumption is much, much more than the large plant. But there is some, and it's a solution for remote area. Some in California, I think the Hearst Castle, and some other tourist area, they use desalination to provide water for the tourists. So it's already implemented. And if you can have renewable energy there, it will be great.
Hi, my name is Christian Junge. I'm a civil engineering student at TU Darmstadt in Germany. And I just have one last follow-up question on to the renewable energy use for desalination. So since we're already dealing with water, have you ever looked into studies or thought about using hydraulic energy to power desalination plants? I mean, there's like very old plants for the Qatar depression in Egypt and in Israel. I can think about similar usages. Again,
reverse osmosis desalination works by electricity. As long as you get it from any source, it's okay. I mean, the point here, I don't want to give you the impression that if you use this renewable energy, then we need to rest and say, okay, this is the best solution. We always need to work toward the reduction of the energy, and if reduce it, you can use the grid and use the renewable energy for some other more beneficial effects. You don't want, for example, you can use thermal energy, and do it by thermal desalination to desalinate seawater, like in Saudi Arabia. but it will not be beneficial. It's better to use this thermal energy to produce electricity, and then with this electricity, you will operate a more efficient desalination plant. So it's, it's just what you do with the energy and the idea that you still need to reduce the energy for desalination. It can operate with any electricity that comes from any source. Now, as I said, if it's fluctuating, it poses some problems, but there are some solutions to it.
All right, well, thank you all for your great questions, and let's thank our speaker again.
Good morning. My name is Peter Gerges, and it is my great pleasure to introduce Professor Bruce Rittmann. Professor Rittmann is the Regents Professor in the School of Sustainable Engineering and Built Environment at Arizona State University. He's also the director of the SVET Center? Sweetie, forgive me, for Environmental Biotechnology at the Biodesign Institute. He's an internationally recognized leader in microbial biotechnology and is known for using microbial communities to address issues in pollution, water treatment, wastewater treatment, capturing renewable energy, and improving human health. He's published nearly 500 peer-reviewed papers, and according to the Institute for Scientific Information, is one of the world's most highly cited researchers. Professor Rittmann earned a bachelor's and master's degree at Washington University in St. Louis and a doctoral degree in environmental engineering at Stanford. He's a recipient of numerous awards and has received many accolades, including the Arizona Bioindustry Association Award for Research Excellence, the American Society of Civil Engineers Simon W. Fries Award, the National Water Research Institute's Clark Prize for Outstanding Achievement in Water Science and Technology, and the Huber Prize from the American Society of Civil Engineers. He's a fellow of the International Water Association, a fellow of the American Association for the Advancement of Science, and a member of the National Academy of Engineering. Professor Rittmann's accomplishments and accolades are many and varied, and I'm certainly been a big fan of his work for many years now, and it is our great pleasure to welcome him here today. So without any further ado, Professor Rittmann.
Okay, good morning. Thank you very much for having me here. It's really a pleasure to be at this wonderful conference and beautiful place. So the talk title is, water is part of the solution for renewable biofuels, not a roadblock. And I'm going to get to the solution part in a few minutes, but the first thing I'm going to do is try to set the context for what we're doing and why this is the right question. So let's begin with what I consider to be the most fundamental sustainability challenge. And again, sustainability really is sustainability of human society as we know it. And in my opinion, it is our unsustainable use of fossil fuels. We use a lot of fossil fuels. I'll give a few numbers in a minute. And we really can't keep this up. And we know that. So on the one hand, of course, we're all aware that we eventually will deplete these reserves, particularly petroleum, and there are tremendous economic and geopolitical crises caused by our dependence on them. But even if a miracle should occur and we can get rid of these problems, we cannot get rid of the biggest one, which is global climate change. The burning of the fossil fuels is simply putting lots and lots of greenhouse gases, CO2 in particular, into the atmosphere. The planet is heating up, the climate is changing, and this is going to cause us all kinds of problems like you can see here: rising ocean levels, lower levels of inland waters, melting glaciers. And the one that's really going to get us as a human society is a huge increase in extreme weather events that we're going to have to deal with, and we're going to get real tired of it. So CO2 is the main driver in greenhouse gases, and so I took from the IPCC information some selected years here with the atmospheric levels of CO2. And, of course, pre-industrial revolution, it was about 280 parts per billion. Industrial revolution started in the 19th century. It started to ramp up already to about 300 in 1870. There's a little gap here in my table. We had a lot of wars in that time, and it kind of slowed economic activities. But after World War II was over, things started to pick up again, 305 and 50, 325 and 7. And you can see it going down the list, and we're now around 390 parts per million. So we're way up, and we're going up faster and faster. The estimates are somewhere by 2050, so 450 to 550 parts per million. This is way high compared to things. Now, the IPCC, august international body, hopes, and this is aspirational, they really hope that society makes some good decisions and we would be able to stabilize things in this 450 to 550 range, which you can see is twice, roughly, pre-industrial revolution. You know, I understand why they do that, but I don't like that as the goal. My goal is, how about 390 is enough? Let's stop here. What would it take to arrest the rise in CO2 where we are now? Well, we can figure this out, and people who are experts at this figured out that there's a year up here that had a fossil fuel use that was about the right level, that if we maintain that level, we would hold steady at around 390. And that year is, everybody thinking about that? It's up here. Yeah, it is. 1950. Some of us in this room were alive in 1950. I was barely alive. And that's my birth year. It's an important year. And those of us who were alive in the 1950s know that human society is not going to go back to the use of fossil fuels at the rate of 1950. We simply are not. It would be catastrophic in many ways, and we aren't going to do that. So the answer isn't just stop using it and go back to 1950. We can't do that. So we need to do something else, and that's where the solution begins. So let's talk about what the scale of the problem is if we're going to come to a solution to this, or at least a part of the solution. And so I have a couple of slides on scale. So here up here is a very important number. Human society today across the planet uses energy for its human activities at about a rate of 16 terawatts. This is the same thing that many talked about, watts. It's just bigger. Tera is a bigger number. So that's a big number here. About 84% of that comes from fossil fuels, that's shown up here. And it's going up. It'll probably be higher. Now the point is, this is actually a very large amount of energy. It's a huge flow of energy coming from fossil fuels, about 13 terawatts worth. Now, more on scale. So there's our 13 terawatts of current fossil fuel use. On the good side, the upside is the sun's sending to the Earth continuously about 173,000 terawatts of energy. Way more than we need for human society. So, in fact, we've got a lot of upside potential of completely renewable energy coming in from the sun. Now, isn't that great? It's great. On the other hand, the other side of the coin, if you look at photosynthesis on the planet, capturing sunlight energy into biomass and look at its energy value, it's somewhere around 140 terawatts. Natural photosynthesis and agriculture are collecting about 140 terawatts. Human society is using it through fossil fuels at about 10%. 10% of that which is captured into the natural and agricultural ecosystems. This is the heart of the problem. We demand extraordinarily high fraction of the natural energy flow through the biosphere. And that's why we're getting more CO2 and we have all the other problems associated. So this is, in this context, 13 terawatts is really a huge, huge number. Now, I work in the microbial bioenergy business, and I think that microbial bioenergy can play a big role in large-scale renewable energy. That's why I do research. That's why I'm here talking today. And there's a big if here on this. And the if is we have to let water work for us, not against us. We're at a water conference. We're talking about water. If we make water the enemy, or maybe we're the enemy of water, this is going to fail. If we make water work with us, we can succeed. So how does that work? Well, first of all, I'll tell you what doesn't work. And that's crop-based biofuels. Corn, of course, is the worst candidate, but all the other ones aren't so good either. They have a bad reputation, and there's a good reason for it. They should have a bad reputation, and that's because they use a lot of water. A lot of this is irrigated, and even if it's not irrigated, we use a tremendous amount of water in agriculture. Agriculture is the #1 water consumer in the United States today, and pretty much the same all around the world. Second, even if we have enough, agriculture, as it's normally practiced, creates a lot of pollution. So we're dirtying up the water, creating a lot of environmental impacts, particularly eutrophication and hypoxia, although we can name some others to go along with them. So we're causing great stresses on water quantity, and we're causing stresses on water quality as we do agriculture already, and if we intensify it, it only gets worse. So that's not the answer. So what could be the answer to make water work with us, not against us? Before I get to that, again, the last piece of the foundation for my talk today, I'm going to give two principles of bioenergy. And then we're going to move forward to what I think is at least part of the solution. So principle number one, very important principle. Ultimately, the sun is the only real significant source of renewable energy on the planet. We have a lot of it, 173,000 terawatts all the time. But it's very diffuse, it's not in a form we can use to drive our car, fly our airplane, and do things like that. So it's not in the right form, although we have plenty of it. We have to get it in the right form. To get it in the right form, we have to understand the second principle, is that the energy is in the electrons. Now, Manny was just talking about all that electrical power that needs to desalinate water. Well, it's obviously the energy is in the electrons in electricity, but it's true for really almost every other form of electricity here. So our goal in renewable energy is to take sunlight, very diffuse energy, it's radiant, and convert it into forms that hold high energy electrons in something that human society can readily use. And I've listed some down here: electricity, of course, methane, hydrogen, and hydrocarbon fuels being things that our society knows how to use. These are wonderful energy forms, and we just like to make them renewable. So how does this look when we combine the two principles together? And here's the schematic over here of it, and the words on the right go along with it, just the same information. So it all starts with the sun. That's where the energy comes from. We have some CO2, so it's in the atmosphere, and we use photosynthetic organisms to capture the energy and electrons from the water and to make biomass. Now they make themselves. We can then use that biomass sometimes directly, consider your campfire, burning wood, or after some processing to produce things like hydrogen, methane, hydrocarbon fuels. We can then use this to generate electricity or motive force to run our society. That returns the CO2 back to the environment. So what we have here is the carbon neutral loop. CO2 comes in, gets energized with energy from the sun and electrons, forms biomass, we go around, we extract the energy out, return the CO2. So this is a carbon neutral loop using renewable energy. This is what we aspire to do, is what we need to do more and more of. Comparing that to fossil fuels, well, it's really the same principle. Fossil fuels, all that hydrocarbons, the coal and petroleum and things, it's all the product of photosynthesis. The same things, that starting left-hand corner I showed you. It's the same principle, but for one thing. The difference is that those fossil fuels were produced hundreds of millions of years ago. And we are now mining hundreds of millions of years of photosynthesis and combusting it in a couple hundred years. So you could see why the CO2 concentration in the atmosphere must be going up so fast, is because of the mining of 100 millions of years of photosynthesis. So what we really want to do is we want to do contemporary photosynthesis, not fossil photosynthesis, and then we have renewable carbon neutral energy, and that's our goal. And also we want to replace the fossil fuels with this contemporary energy. It's renewable, and then we satisfy all criteria, including many's desire to have renewable energy as the source for the grid. Okay, so the idea is to replace fossil fuels with this renewable energy using this format. Now, one last piece of perspective, and that is residual biomass. Nature and the agricultural system do a lot of photosynthesis. There's a lot of what we call residual biomass. If you think of agriculture, you've got agricultural residues, you've got food processing waste, animal waste, and things like this. If we could collect all of it, yeah, we can't, but if we could collect all of it and convert all of it to energy, we could satisfy roughly 25% of the Earth's humans' energy demand, roughly. We can't do that. We can't get that much, and we wouldn't want to do it, but it's a significant amount. But the key thing is here, this is not nearly 2/3 of our human fossil fuel use. It's important. We should be doing this. We do it in our center. We work on this, but it is not going to achieve the solution that I'm talking about. So residual biomass is not the answer. So yes, residual biomass is not enough. And so the conclusion is, if we want to implement the solution that I've been talking about, is we need a lot more biomass. We don't have enough biomass. We need to carry out a lot more photosynthesis, and we need to do it in an environmentally acceptable manner. And that now starts the story about what might be a good part of the solution to renewable energy in the future. So we want to do more photosynthesis. Who does photosynthesis? We have plants that do photosynthesis. You recognize those. And we have microorganisms that do photosynthesis. Maybe you don't recognize those. I'll tell you some about those in a minute. So we have algae and photosynthetic bacteria. Which one should we choose? Should we choose plants or should we choose microorganisms? Well, I've made a little list here, 7 bullet point comparison of photosynthetic plants and photosynthetic microorganisms here. 7 points, they're lined up. I'm not going to talk about all 7 because I don't have time. Just a few highlights. So first of all, let's talk about the use of arable land, the land on which we grow our crops for food. Of course, if you're going to grow plants, you have to grow it on arable land. That's by definition. Microorganisms, on the other hand, don't grow in soil. They grow in water slurries, and you can put them anywhere. So there's no competition for arable land when you use microorganisms, since microorganisms don't grow in the soil. 2, how about the aerial productivity, how much we can produce? If you look at the productivity of different types of biomass, depending on the type of biomass and the comparison of organism, the rate of output of biomass, product of photosynthesis, is somewhere between 10 and 100 times higher for microorganisms compared to plants. Plants are really quite inefficient at collecting solar energy and turning it into biomass. They produce some neat stuff, but it's not at a very high rate. Microorganisms are much, much faster, and when you go 10 to 100 times higher productivity, you start getting in the realm where you can conceive of producing terawatts worth of biomass energy using microorganisms. Third, you have the issue of requiring water and fertilizer. And of course, we know the agricultural system uses a huge water user, biggest water user in the country. And by the way agriculture is practiced, you get a lot of pollution from nutrients and other things. You don't have to do that when you're using microorganisms. You don't have to be big water users. You don't have to have actually any pollution from minerals and other nutrients if you do it right. And so a well-designed system here can avoid completely the competition for water quantity and quality. So when you add them all up, it's obvious to me that we should be going with microorganisms for our renewable biofuels and skip plants totally, except as we have residuals from them naturally in the food system, and we should use those, of course. So now I'm going to tell you about some things that we are doing to try to implement this idea of using microorganisms to produce renewable energy from the sun. And the first thing I'm going to talk about is what I call new biomass or biopetrol from photosynthetic bacteria. So we have a very large research program at ASU exploiting the cyanobacterium sinicacystis. Here's a picture of sinicacystis. This is of a couple of micrometers across here on it. It's a bacterium, that's not algae. It's a very simple microorganism in terms of its genetics. It's very well understood. This is a big advantage of it. It's a very robust, fast-growing organism. It's also an organism that naturally contains a relatively high amount of lipids. And you can see that in the picture. If you look at the picture here, you can see all these lines running through here. You can see they're running around here. Those are what we call the thylakoid membranes. That's where the organism puts the apparatus to collect the sunlight energy and convert it to chemical energy. So an organism, Seneca cystis, that's growing very well, it's very happy, is loaded up with membranes. Membranes are mostly lipids. Lipids are oil. You get the idea. So we produce these organisms with a lot of lipids. We can harvest the lipids, and we can use this as a substitute for petroleum for a lot of the transportation fuels. This is an organism that is genetically tractable. It's completely well understood. We can modify it to help it do this job for us, that is making lipids better than it would naturally do. And we are working on that aspect. And of course, we also use some very modern engineering tools, bioengineering tools, that's stuff I work on, to create the systems we call the photobioreactors that make this happen in practice. So here's some pictures of it. Here's the organism again. Of course, there's our little schematic of the photobioreactor. But here are some real ones that we are using. Here's one that we use in the laboratory. It's 16 liters, very highly monitored and controlled, good for very careful fundamental studies in the lab. Here's a picture of one that's outside, about 2,000 liters on the roof of one of our buildings that we can use for field studies and test it out there in the real world conditions of the Arizona sun. So the value proposition, as I've just explained it, is this. We're able to create, under controlled conditions, a lot of new biomass. Now notice I wrote it in green font. You got the idea? It's photosynthetic new biomass, and we can use this to supplement the normal capture of biomass from agriculture and nature here. So we do this under controlled conditions here. So we become what could be viewed as kind of a solar-powered factory for renewable energy forms. And because of the high productivity per unit area, we could actually approach multiple terawatt levels of production, at least in principle on it. It's not impossible. It doesn't say it's easy, but it's not impossible. So we could do it. And so what we do is the lipid part we can capture and take them off to make transportation fuels, and the rest of the biomass we can get the energy value out into other useful forms like methane, electricity, and hydrogen. Now let me show you what that looks like graphically. Same information basically, but in a very nice graphic format. So here's a picture of what I call an integrated water and microbe-based bioenergy system. So first of all, I want you to notice there's a loop here. It's a loop. Okay? So this main action is going on over here. So this begins with sunlight and CO2. So the sunlight, of course, comes from the sun. I'm showing the CO2 from a power plant. It could come from the atmosphere itself. But anyway, some CO2 input coming in. We have a photobioreactor in which we're growing the organisms. We make the new biomass. It comes over here. We extract out the lipid portion that goes off to make transportation fuels, jet fuel, diesel fuel in particular. The rest of the biomass then comes around here, and we go through a couple of steps of fermentation and extraction of energy. I show a microbial fuel cell here to make electrical power, but you can make methane or hydrogen or something else even over here. Extract all the energy out of all the carbon on this side, and then here, once you get to that point, you're left with the water and the nutrients, mainly nitrogen and phosphorus, which you just recycle. So you see, everything is going around and around and around the loop. The water goes around the loop, the nutrients go around the loop. What comes in is renewable energy from the sun and CO2, and what comes out is a couple of different forms of renewable energy. Energy in, energy out, everything else around the loop. Yeah, pretty neat idea. So, that was pretty good, don't you think? Yeah, I think so. But I got something better. We've got another step that we're working on. It's even better if we can make it work. It's a second strategy here, just to introduce that. We're trying it another way, and that is to have the photosynthetic bacteria pump out the feedstock. So we don't even have to harvest the organisms. but we harvest the product. So we have now a large ARPA-E, this Department of Energy project on this. So we still use sunlight and CO2 as the prime resources. We still use cyanobacteria to do the job here, but they produce the product, and we can avoid the hassle of having to harvest the organisms and squeeze out the lipids and all that kind of stuff, which is actually technologically not so easy to do. So it looks like this schematically. Here's the organism here. We do some genetic modifications here. So this organism will take in carbon dioxide, light, in water and produce things like fatty acids. This is a precursor to things like jet fuel. It can produce other things too, but we're focusing on this one right now on it. The strategy looks like this. You take over here the normal photosynthetic pathway of the organism. They fix CO2, they make various things, acetyl-CoA, fatty acid materials that they normally use for lipids. We added a gene here that diverts the flow of this material instead of to lipids over here to fatty acids, like lauric acid or palmitic acid, shown over here. We then harvest those and we can convert them with a lot more ease to the transportation fuels like jet fuel and diesel fuel. There's a picture of some of the lauric acid coating the flask here. That's, of course, not how we would normally harvest it, but it's good for the picture so you can actually see it's being done. So in the second strategy, what we're doing here, we do all these good things in the water, and we don't really need to input nutrients because we're really not producing biomass. And we don't need to harvest and convert the biomass because we're really not producing biomass. We're letting the biomass produce the product. And this becomes truly a photosynthetic factory. The organisms are themselves a little factory run by the sun, converting CO2 into useful products like this. And so the analog are chickens. Chickens, right? You want to have an omelet. You don't go and kill the chicken to get the eggs from out from the inside. You let it lay the eggs, and you harvest the eggs. So, it's like a chicken. Photosynthetic chicken. Okay, I'm at the end, and I'm just going to sum up the main take-home lessons here from my talk today, and then we'll have some questions. So the first take-home lesson is we really need a lot of energy. We use a lot of energy, and we need to replace fossil energy with renewable energy at the terawatt level. Many terawatts of energy need to be replaced. So we get the same good services, but we don't need to keep using so much fossil fuels. Photosynthetic microorganisms can stand at the heart of this, not all by themselves solving the problem, but they can be a key component in doing this because we can produce high-value biomass, and because of the high aerial productivity, we can do this at rates that can approach terawatt levels. And we do it in the water slurry. We don't do it in the soil. So we can create in this a closed loop where the water and the nutrients are cycling around, and we just have energy in and energy out. Diffuse sunlight energy in, concentrated useful energy out from the system. So in this way, it's all done in the water. We are letting the water work for us, not against us, to generate enough renewable energy to help us replace fossil fuels and make our human society a lot more sustainable in the decades to come. So thank you very much.
We have time for questions. Looks like you're all queuing up.
Queuing up, very efficient. Please.
Hello, my name is Ramon Sanchez. I come from the Harvard School of Public Health and the Harvard Extension School. And my question is about what are your procedures, to make sure that some of these species, like Synechocytis, that is extremely aggressive, that they don't pollute large bodies of water, We have been farming microalgae here for 10 years, and every time that we want to go into large scale, wastewater treatment or something, the municipalities are extremely concerned about that particular issue, that some of these algae strains may invade large bodies of water or rivers or the ocean. So what are the safety protocols that you have in place for that?
Okay, so I'm going to answer that in two parts. I mean, for the first part, and that it has to do with the direct answer about what safety protocols. As I described in my talk here, this is basically a closed-loop system. And so we're not just letting things get out. I mean, we do produce some biomass in these systems, and it's harvested and it's under control, and it goes off to do what it should do to make energy on it. So we're not just letting these things out into the environment, and these are closed systems. The second thing, of course, is that if you look at the problems that can be caused by these kind of organisms out in the environment, the organisms aren't the problem. What's the problem is the pollutant discharges that lead to their proliferation where we don't want them. And so these are nutrient discharges primarily that cause proliferation of these organisms and lead to hypoxia and eutrophication and other bad things. So it's really not the organisms that are a problem. They're just living. They're not harmful themselves, but they can create some effects. So if we really want to be effective in not having problems, environmental problems with these kind of organisms, we have to do a better job of controlling discharges of nutrients from agriculture and wastewater treatment plants and things like that. Okay.
My name is Marion Moore. I'm from Wellesley College, and I'm struck that your photosynthetic chicken is a single species, and we know from farming practices, both on land and in the oceans, that monocultures are vulnerable to diseases and extreme weather events, which you just mentioned early in your talk. So I'm wondering how vulnerable this is, given that it's a monoculture, and are there efforts to look at polycultures, communities of microbes that might sustain each other?
Okay, that's a very sophisticated question, thanks. So there are two angles on answering it. I mean, the first thing is that these are not monocultures in reality. Anything at the scale we're talking about, and I'm talking about even in the laboratory scale beyond a flask, are never pure cultures. There are other organisms in there, and our center spends a lot of time studying who are the other organisms in there and what are they doing and who are the good guys and the bad guys. So it's always a mixed culture. This is the way it is in all environmental biotechnologies. But even more important is, I think, the issue of, well, would we be wise to have, say, a range of organisms in our system doing either the same thing in a slightly different way or doing different things? And I'm in agreement with you. I think that's a good strategy. In fact, that is exactly what we're beginning to focus on right now, is that kind of a strategy. And there are not only ecological benefits, but there are economic benefits if you, say, produce different products and things like that. So we're right on target with you on that.
My name is Burl Hartman. I'm director of the New England chapter of a group called Environmental Entrepreneurs. And my hat's off to you for coming up with this seemingly very efficient and sustainable method of creating the fuels that we need. My question is, have you or anyone looked at the issues of commercialization and scale-up? We had a very similar, I'm sure it was a different organism, but we had a similar company here called Green Fuels. They had a lot of venture capital in them, and ultimately they failed because they could not successfully scale up to commercial levels.
Yeah, that's, again, right on target. So, technically we can do these things, and now the issue is, can we do them at large scale and at a price that anyone's interested in? And so it's all scale up, it's engineering and materials, and yes, we spend a lot of time on this. I did mention towards the end of my talk that we have an ARPA-E grant from the Department of Energy, and they are really emphasizing this and making us emphasize it. So even if we didn't want to, our sponsor is going to make us do it. But we are, and we are developing partnerships with different types of companies that can bring in different components to help us make this more efficient and more cost effective. If we had to do it today, if somebody told me, go out there and build a big one and make so much stuff, it would be really expensive. And so we're not ready to do it today. We don't have the materials and the technology together to do it at a cost effective manner. We could make it work, but we wouldn't make it work well. So you're right on target. This is the weak link. It's going to take at least some years of continual research development and scaling up before we're ready to make this commercially interesting. And so we face the dreaded valley of death syndrome here, and we try to keep moving forward and eventually get past it.
Thank you. Hi, Joan Ruderman, Harvard Medical School and the Radcliffe Institute. Thank you for a wonderful talk. Many of my questions were posed by people in front of me, but one of the great things about going to a talk way outside your field is you get to hear new words. So I'd like to ask, what is lignocellulose? What is it and why does it matter? It was on one of your first slides as a comparison between...
Oh, lignocellulosic.
Yes.
Okay, yeah.
You even get to
Okay,
learn how to
thank
pronounce
you.
these words.
Okay, that's great. Yeah. Okay, so lignocellulose is a very complex material that plants use, and you can simply think this is how it allows them to stand up and stay intact for a long time. So it's a complex of lignin and cellulosic different polymers get all wound together. It's designed, if you want to anthropomorphize things, is designed to make the plants resistant to falling apart. And so this is a great thing if you get a tree and you like your tree to last and stand up. It's not a great thing if you're trying to convert the plant material into bioenergy, where you've got to break it down into simple things that can be converted to our final products. So one of the huge drawbacks of using plant materials that are not like the corn kernels is that a lot of it is lignocellulose, and it's really hard to break it down. And so this is anyway. So the point is, microorganisms aren't plants. They don't have stem stalks and all that. They don't need any lignocellulose. They have no lignocellulose. So their biomass in microorganisms is much more readily available to break down and convert into energy.
Great. Thank you very much. One more question?
One more? Okay, last one.
My name is David Glader. I represent the concerned citizens of Russell, Massachusetts, who are opposing the construction of a wood-burning power plant on the Westfield River. All of this process that you've described generates fuel that would then presumably be oxidized in an industrial power plant. Those power plants use up a lot of river water. They produce a lot of carbon dioxide. How are you addressing those problems?
Yeah, okay, so there you raised two specific issues about taking the fuel, the hydrocarbon, now carbon-based fuel that we've created. It was renewable when we created it, and now you're going to combust it to make the actual energy, say electricity. So you mentioned two things. One was CO2 and the other one was water use. Okay, the CO2 one is really not a problem, because remember that CO2 just came from the atmosphere and we're just putting it back. So we're not adding to the atmospheric load of CO2 in any way.
No, you're not making it worse.
We're not making it worse, and we're making it better to the degree that we are displacing the use of fossil fuels. So this system only really works to make things better by replacing fossil fuels with our fuel. If we just keep using more fossil fuels, and then we aren't making it better. So we must replace. This is really a take-home lesson. We must replace fossil fuels in order to get the benefits in the global climate change. The other one is water use, and you're 100% right. Whenever you combust it, you generate a lot of heat, and there's a lot of water consumption, or at least water throughput on it. And anytime you combust it, that's the way it is. And so we are also investigating methods in the conversion thing. I'll go back very quickly here. Over here on the left side, where we get the energy out without combustion. So if you make either hydrogen or you make electricity directly over here by what we call microbial electrochemical systems, you can create the energy and there's no combustion, it's low temperature, and you don't have this temperature problem.
Can you say how far along you are on these alternative energy generation processes?
They're in a similar state of science and technology development as these photo bioenergy things. We're making very rapid progress, but we're nowhere near having this ready to go out and sell it for large-scale systems. But it's going very quickly. We just created a company to develop this, commercialize this particular thing, so we're very enthusiastic about it.
Thank you.
Thank you.
Hi, Ron Swag. I'm from Woods Hole, and actually in 1978 I served on a Congressional Office of Technology assessment panel that looked at the conversion of energy from algae and from plant material to biofuels. And at that time, basically looking at the laws of thermodynamics and other aspects with regard to the basic physics of this, and the critique that was done by Kress and Dimitrov from MIT relative to what you can expect to get out of the energy relative to what goes into it. So the basic balance of energy equation. And the notion that I've read and understood at the time is that it takes more energy actually to get the energy from the material than you get as a result of the process. I just wonder if your research has advanced that.
I've heard about those analyses, and probably if we had to do it at large scale today, it probably would be the answer, and obviously we aren't going to do it that way. And so, yeah, I mean, there are various things we're doing to minimize the operating costs, the energy to run the system and to harvest and convert the product. Now, when I talked about my second, it's gone. The second strategy, one of the goals for that was to eliminate the economic and energy cost of all the downstream processing. If you produce the product and it doesn't need all these extra steps to get it to a useful material, you really cut down the money cost and the energy cost a lot. So we've targeted that specifically to the issue that you've raised.
Thank you. Thank you all again for the great questions, and let's thank Professor Rittmann one more time.